So, have you ever stopped to wonder why you can upload a super complex photograph to a modern AI, ask it highly detailed questions, and yet, when it replies, it can only ever give you words back? Why can an AI read an image perfectly but only reply in text? It feels kind of like a one-way street, right? I mean, you can upload a picture of a broken bicycle and get a step-by-step text manual on how to fix it, but the AI can't just generate a visual diagram showing you exactly where the wrench goes. That fundamental friction, that invisible wall developers face with current AI multimodality, is exactly what we're unpacking today.
Okay, let's dive into this, because to really understand the solution, we first need to look at the villain of our explainer today, the older adapter-based vision language models, things like Lava or Blip2. Treating text and images as two completely different entities basically creates three major headaches. First, the model can only consume images, not emit them, so the output is stuck entirely in a text-only world. Second, handling mixed-modality documents is just incredibly awkward. Imagine trying to prompt an AI for a baking recipe, and you want it to actually show you a generated picture of what the dough should look like halfway through. You'd either have to pause the whole generation, call a separate image tool, and stitch it all together manually, or just accept a super clunky workflow. And third, there's a distributional mismatch. Because the visual tokens and the text tokens literally live in completely different mathematical neighborhoods of the model's brain, it creates these really subtle, frustrating alignment issues.
Welcome to the Explainer. Today, we're looking at a massive paradigm shift that completely rejects that old premise and changes the rules of the game. We're talking about Meta's Chameleon model from May 2024, which introduces the incredibly powerful concept of early fusion, token-only multimodal models.
Here's a quick roadmap so we know where we're headed. We'll start with the multimodal disconnect. Enter Chameleon's early fusion, look at the VQ-VAE image tokenizer, uncover some secrets to training stability, and wrap up with early versus late fusion.
Let's start with Section 1, the multimodal disconnect, or essentially the wall developers just keep hitting.
Think of the old way of doing things, late fusion, a lot like two trains running on completely separate tracks. Text goes down one path to be embedded, while an image goes down a totally separate visual path, and they only finally meet at the very end inside the large language model. Their vocabularies never actually overlap. But Chameleon's thesis flips this entirely with early fusion. Instead of separate tracks, what if images were just sequences of discrete tokens sharing a universal track with text? They'd use one shared sequence and one autoregressive loss from the very beginning. And that technical term just means the AI only has one single job, predicting the very next token in a sequence, whether that token happens to be a word in a sentence or a puzzle piece of a picture.
Which brings us to Section 2. Enter Chameleon and the magic of early fusion, the real aha moment that unlocks mixed modality generation basically for free.
And this brilliantly illustrates the exact definition here. Early fusion means images are converted into discrete tokens that share the transformer's exact vocabulary right from step one. A really great way to think about this is true bilingualism. Instead of having one brain for English and a completely separate external translator for Spanish, the model is just naturally perfectly fluent in a single universal language. Pixels and letters are just different characters in the exact same alphabet. So every document becomes one fluid sequence. Text tokens and image tokens interlead seamlessly by one system.
So how do we actually pull off that translation? Let's move to Section 3, the VQ-VAE image tokenizer, and see how this actually works under the hood.
To turn a continuous, fluid picture into discrete text-like puzzle pieces, we use a vector-quantized variational autoencoder, or VQ-VAE for short. Let's walk through this pipeline organically. Step 1 is the encoder. Think of this as a highly advanced scanner, taking an image and mapping it down to a grid of spatial features, like a 32 by 32 grid. Step 2, we bring in the code book. This is basically a massive universal paint palette or a visual dictionary. Then comes Step 3, quantization. For every single feature our scanner found, the AI looks through that visual dictionary to find the absolute closest matching color or shape. Mathematically, it's measuring the shortest L2 distance between vectors, but practically, it's just snapping a complex, continuous pixel down to a simple integer ID number. Finally, Step 4, the decoder takes over. It looks at that list of ID numbers and acts like an artist painting by numbers, mapping those quantized integers right back into a recognizable image.
Now, what's really interesting about this is the scale. To make this universal language work, we need a set vocabulary, and the magic number Meta landed on is exactly 40,192. That is the size of Chameleon's final shared vocabulary. Let's break down exactly what makes up that 40,192, because it's a really fascinating balancing act. You've got 32,000 standard text tokens, which gives the AI a massive, nuanced grasp of human language. Then, you have 8,192 codebook entries specifically dedicated to image tokens. That's the sweet spot right there, giving the model just enough visual puzzle pieces to construct complex images without completely overwhelming its memory. And finally, you have the crucial addition of exactly 2 modality separators. Because it's a single ID space, the input layer maps every single token to a hidden vector in the exact same way.
Those 2 little separators matter immensely. The image and /image tags bracket the image token sequence, acting exactly like stage directions in a script or HTML tags on a web page. They're invisible cues telling the system, hey, stop typing words, grab your paintbrush, we're doing an image now. So at generation time, if the model emits an image tag, the software instantly knows the next tokens are those visual IDs that need to be sent to the decoder to render pixels. The model picks the order completely autonomously. It can output text, then an image, then more text, all in a single uninterrupted breath.
But getting this to actually work, it is not easy. Let's look at Section 4, Secrets to Training Stability, or how Meta tamed a 34 billion parameter beast.
Here's the thing. When you start training a massive early fusion model, things get highly unstable very quickly. In fact, without some serious engineering magic, Meta found their 34 billion parameter training runs were completely diverging, just crashing at multiple checkpoints. The root of the problem is that image tokens act a bit like bullies in the training data. Because images are so densely packed with information compared to text, the mathematical gradients from the image side just start to dominate and overpower the text learning. To fix this, the paper details 3 vital engineering breakthroughs. First, they introduced something called QK-Norm. Second, they had to be incredibly strategic about dropout placement, putting it after every single residual add for extra regularization. And third, they adjusted LayerNorm ordering, literally adding an extra LayerNorm on the skip connection of the final block to keep the whole gradient flow stable.
I want to zero in on that first trick for a second, QK-Norm. This stands for applying LayerNorm to the query and key projections inside attention right before their dot product. Why is this so absolutely crucial? Because it completely prevents something called logit magnitude explosion at depth. Now, if that sounds like totally impenetrable deep learning jargon, just think of it like microphone feedback at a concert. A small mathematical signal loops, it gets louder and louder through the network's layers until it literally shrieks and breaks the whole training process. QK-Norm acts as a volume limiter. It stops that feedback blowup dead in its tracks.
But of course, there's a catch. The VQ-VAE tokenizer we discussed is inherently lossy. When you compress a high-resolution image into just a handful of tokens from a vocabulary of 8,192, you are inevitably going to hit a quality ceiling. The reconstruction metric, called PSNR, caps out around 26 to 28 decibels. In practical terms, it means the generated image looks a bit like a compressed JPEG from like the early 2000s. It's recognizable for sure, but it falls visibly short of those continuous space diffusion models like Stable Diffusion 3, which achieve 32+ decibels and make those hyper-crisp 4K photos. In this architecture, the tokenizer itself is the primary bottleneck for image quality. It's the ultimate trade-off of the early fusion approach. So when should developers use which approach? Let's bring it all together in Section 5, Early versus Late Fusion. So the crucial point really comes down to a developer's dilemma. If your product relies on interleaving text and generated images fluidly, say an AI that writes a children's story and illustrates it paragraph by paragraph in real time, you absolutely must pay the computational tax of early fusion. You get mixed modality generation, but it's expensive, and you're capped by that tokenizer quality ceiling. On the flip side, if you just want an AI that can analyze a screenshot of a spreadsheet and give you a text summary, stick to late fusion adapter models. They're computationally cheap, they just need a single forward pass, and there's no tokenizer bottleneck for pure visual understanding. Basically, pick early fusion for generation and pick an adapter for understanding. Let's move on and see how this builds into the future, because the industry is already iterating on this paradigm super fast. Beyond Chameleon, we have models testing these exact same limits. Adept's Fuyu, for example, skips the separate vision encoder entirely. It just feeds raw image patches straight into the LLM as if they were tokens. It's simpler, though it sacrifices the generation capability. But then there's AnyGPT. This extends that exact shared vocabulary trick we just talked about across 4 modalities: text, image, speech, and music. That is literally awe-inspiring. It means one single AI brain could theoretically chat with you, draw you a visual diagram, speak to you with a human-sounding voice, and compose a background music track, all in one continuous autonomous breath. Which leaves us with a pretty loud final thought.
As we push toward 4K image generation, which requires a massive exponential explosion of image tokens, what's going to break first in a single vocabulary model? Will we simply run out of context length? Will tokenizer quality just completely fall apart trying to capture high details? Or will the system's short-term memory, the KV cache, buckle under the weight of millions of tokens? It's a fascinating question, developers are racing to answer it right now, and the solution is absolutely going to define the next generation of multimodal AI. Thanks so much for joining me on this explainer, and keep questioning the limits of what we can build.